Stand back. I'm going to try science. Hello Internet, my name is Quinn and this is Blondihacks. I'm back on the big steam engine project and I'm going to make the flywheel. Always an iconic part on a steam engine, and once again the size and the mass of this thing is really going to push my little machine tools to their limit. So we'll see some more creative solutions today, so let's go. Alright, here is the flywheel casting and it is a monster. It is 7 inches across and I think it weighs probably 15 or 20 pounds. It's very, very substantial. It's definitely the heaviest thing I've ever had on my lathe. And well, how am I going to fixture this? Just kind of mocking it up here visually to see if it's possible to machine this on my lathe, and it looks like I can, though certainly not in a chuck. The real problem though is actually back here. Ignoring the change gears for a moment, this is the basic drive system on a Chinese lathe. You've got a V-belt here of sorts, and it's just one gear reduction from the motor to the spindle. And this is really the problem, because DC motors don't have a lot of torque at low RPM, and low RPM is what we need for a large diameter part like this. In fact, the desired RPM for 7 inches of cast iron with high-speed steel is actually 50 RPM, which is very slow indeed. Sidebar on import machine tool drive systems, because they're pretty interesting. This is not a standard V-belt. As you can see, it's a 60-degree angle on the pulley and the belt. A normal V-belt is between 30 and 40 degrees. These are Gates Polyflex 60-degree V-belts, and this is such a niche and new standard that Machinery's Handbook just says, yeah, this isn't really a standard, so we're not going to talk about it. It was apparently developed specifically for high-speed, medium torque, compact drive systems such as small machine tools. In fact, I think they're also used in snowblowers and a couple of other very niche applications. The belts are fairly easy to get. The pulleys, though, are unobtainium. Try to find 60-degree V pulleys. I dare ya. So if you're going to mess with the drive system in your lathe, plan on making pulleys. Alright, enough of that foo-fa-ra. Let's get back to the flywheel here. I'm going to set it up on the faceplate. And in order to clamp this thing down, I want to clamp it by the spokes because I want access to that inner rim there. So I'm going to use these pieces of square bar. They seem like good clamps, but they're a little too bulky and I only have 2 and I need 4. So I ran over to the bandsaw and sliced those down the corners to make 4 little pieces of angle iron. These are going to be my clamps. I'll mark and drill some clearance holes here to line up with some threaded holes that I have in the faceplate. And this is the perfect opportunity to bust out my newest tool making project, the float lock vise. Hopefully you watched this series on making one of these. I wasn't sure at the time if this thing was going to live up to the hype, but I gotta say it sure does. I'm really, really enjoying using this thing. You can see for parts like this, which are very typical of the kinds of parts I make, it's just exactly perfect. I can use those shoulders at the top of the jaws to hold a thin part here very easily. It's very, very quick to get the vise set up into position. Holds the part very securely. And for making a lot of similar parts like I'm doing here, it's great because it just takes a quarter turn to loosen that part and remove it, and a quarter turn to put the next one back in, and away you go. So if you're thinking about buying or making a float lock vise, I definitely recommend it. I really enjoy using this thing. It works super well. Back to the faceplate now. I've got some threaded rod here. You know, for the cylinder casting, I drilled and tapped these 1/4 holes in my faceplate, and gosh, I wish I'd done that years ago. Faceplate setups are so much easier having small threaded holes in your faceplate like that. So if you're worried about drilling holes in your faceplate, I gotta say strong recommend for that. With the hardware still loose, I'm checking for wobble here. Of course there is some. The casting might be warped or the back side of it might just be uneven, but you don't want to clamp it down in this position because you'll introduce warp into it, then you machine it flat and then release the clamps and now your machined surface is warped. So you got to shim the back of it there so that there's no rock in it before you clamp it down. I'm just doing this by trial and error with shim stock in different places until I can feel no more rock in that. And then we can clamp it down with confidence that when we machine that flat and then release the clamps, it'll stay flat. I'm also roughly centering it on the faceplate here. That'll make the dialing in process a lot quicker. Usually with the scale there, you can get the part within 20 thousandths or so of run out. Now we can put this whole setup back on the lathe, and it's time for the fun part, which is dialing this thing in. Dialing things in on the faceplate is never super easy, so plan to take some time with this part. Let's see how we did right off the bat there, and it's actually not too bad for, you know, quote-unquote dialing it in with a scale. My secret weapon for this is this guy here. This is a Brown & Sharp button indicator with a lever arm on the back of it, which allows me to indicate effectively sideways on a surface. This was something I found on eBay. It was actually in a box of indicator parts, and I saw this in the photo and knew what it was, and I jumped on it. Got a great deal on this thing. Really, really like it, and it's the perfect solution for this because I need to indicate on the inside cast rim of the flywheel, but also between my clamps there, and this is really the only way I think you might be able to do it. So what I'm doing here is just putting that lever arm up against the cast surface, then I loosen all the clamping bolts just a touch. It still has to be held in place, but you need to be able to move it with the tappy tap tap hammer. And then I dial in the cast inner rim of the flywheel here as best I can. Indicating in the inner rim of a flywheel like this is the key to having a good looking result, because it doesn't matter what happens with the machined surfaces. They're going to get machined and they'll be true no matter what. But the inner rim will not be machined, and if you don't get it running true before you machine the outer surfaces, then the hub and the spokes are going to look like they're wobbling when the flywheel is running, even if everything is technically running true. Now it is a cast surface, so you can only do what you can do. I got it within probably 0.008 there, and hopefully that'll be good enough. A quick eyeball test here shows that is running quite well. You can see the bore in the center there is running out quite a lot, and that's going to make some fun for us here later, but the other cast details are running well. It's important to look straight on when you're doing an eyeball test like this, because this casting does have a lot of planar runout, but we only care about axial runout here because the planar runout is all going to be machined away. And if you don't look at the part straight on, your eye can't really distinguish between planar runout and axial runout. I'm going to start with that bore. So I've got a boring bar here, and I'm just making sure I've got enough reach there to get to the back of the bore, and I got to make sure that when I'm all the way in that all my clamps and everything are going to clear. Got to be very careful with faceplate setups because the part and the clamps might hit your carriage or the cross slide in ways that you never had to worry about with a chuck setup. So definitely be careful about that. This is looking good, so I do a quick feed in by hand to make sure there's no surprises in there, and then I start dialing in some depth of cut and letting the lathe do the work. At the start of this, I was pretty positive that boring this out was not going to go well for the simple reason that A, you can see how off-center the core is there, and that in itself is not that unusual. Cores are never very centered. However, the initial diameter of that core was only 10,000ths larger than the final machined diameter of this bore is supposed to be. And that is very, very close. I've never seen a casting that is within 10 thou of the correct dimension right out of the foundry. I don't really know what they're thinking here, why they make that core so large, because you have basically no hope of cleaning that surface up and not blowing the dimension. But, you know, I have no choice, I have to clean it up, so I just machined it down until I reached this point here where it's almost entirely cleaned up, but I can pretty much tell it's already oversized. Quick check with the bore gauge, and yeah, I mean, we're 30,000ths oversized, and the surface isn't even cleaned up yet. So that means we're definitely going to be putting a bushing in this. The next step then is to do the math on how big the bushing should be. I calculated the diameter of the crankshaft plus 2 times the thickness of the key so that I have enough material in my bushing that can completely enclose the keyway. That's important. And I also don't want to remove too much of that cast iron. I want to leave as much of the cast iron as I can. I landed on 800 thou for that. With the bore done now, I'll do the outside of this boss here, which is mostly aesthetic, but it looks really nice if you clean these up. So I'm going to use the boring bar for this again, and to find the depth, I'm just looking for a spot where I'm grazing the tops of all the spokes. So I do that by hand. Then I set a dial indicator zeroed on this spot so I can come back to it on each pass. And for this, I'm running the lathe in reverse and cutting on the back side, as you see here, with the boring bar. That allows me to get in between all my clamps and stuff. I can't take heavy cuts though with this because my lathe doesn't have a lot of power running in reverse and the motor has a tendency to overheat, so light cuts it is, but luckily we're just cleaning up that surface there. Easy peasy. To face the front of that boss here, I can reach in there with a normal turning tool, but once again, being very careful to make sure all of my clamps and everything are going to clear, and it's going to be close, but I can just get in here with this, so I'll face off the front of the boss like so. What's cool about machining castings is that the more features you machine, the less run out you see in the overall part. When you start out, everything is running out, and then as you machine surfaces, less and less things run out. Perfect example is this chamfer here. There's a little bit of a casting edge left after doing those two outer surfaces, and then the chamfer removes the last little bits of it, and now everything looks to be running true. And that turned out nice, so now let's get to the tricky features, the outer parts. Reach is a challenge for all the outer features on this part because it's so much larger than, well, anything I've ever turned, and it's right near the limits of what this lathe is capable of. But with enough manipulation and the right tool stick out and everything, I am able to reach the OD here, and I'm going to start by facing the front of the rim there of the flywheel. Because of the large diameter out here, the surface is running very, very fast. Back at the top, I mentioned how torque was going to be my problem here because of the diameter of this part. I can't run the lathe at the 50 RPM that high-speed steel would need for this diameter because at 50 RPM, this lathe has no torque and it's just going to stall and blow fuses. That's certainly been my experience turning parts like this before. So my solution is what you see here, and it's the miracle of carbide. With carbide, the correct surface speed for cast iron is much, much higher. The math says I should be running this about 500 RPM, which that's super fast, so I wasn't running it that fast. I was running about 225, 250, but as you can see, the carbide is doing a bang-up job at that speed, and that surface is flying. I had a lot of hot cast iron to wash out of my hair after this project, let me tell you. For the outer diameter, once again, many gymnastics required to find a position for all the slides and the tool post and the tool such that I can reach the back of the surface there, and none of my clamps or anything are going to hit any part of the cross slide or the carriage or anything else. I was, again, right at the limit of what I can reach here with all these tools, but as you can see, this turning actually went really well once I got that all set up. I've long said on my channel that high-speed steel is ideal for beginners, and I do still believe that. I think it's an essential skill to learn to grind high-speed steel, and I think it's an economical and educational way to start for beginners. But there are certain situations for which carbide is just really a miracle thing, and this is a perfect example of that. There's really no way I could have done this part with high-speed steel. The high surface speed of carbide put my lathe into the RPM range where it has usable power, and that was what I needed to solve this problem. So just because you see me using carbide on this channel doesn't mean that I still don't love high-speed steel. It's worth noting here that it would be traditional at this point to put a 2 or 3 degree crown on this flywheel, which means there's a peak in the center of this, and that's so that you can drive things with a flat belt. A peak in the center of the pulley causes the flat belt to track in the center of the pulley. You don't need physical sides on a pulley to wrangle the belt, you just need a peak. However, as you can see, I'm struggling just to turn this at all, so I don't have the luxury of getting fancy with angles on the compound and such. Maybe I can do that later, but I don't intend to drive things with a flat belt off this flywheel anyway. That carbide did a beautiful job. That surface is really nice. I don't think I have to do anything else to that. So I am going to clean up that corner though. You can see some little chips and marks remaining from the casting surface. So I'm going to put a light chamfer on that just to clean those up. Those will be the last little bits of visual run out in the flywheel. So I just basically run the chamfer tool until I don't feel any more of those little chips running over the tool. I don't want to chamfer this too much. It starts to look a little silly if you chamfer it too far. I have my Noga material detector set up here. Let's see if this is authentic cast iron, and yep, it sure is. Everything looks mostly running true now, except for the inner rim there is still visually running out a little bit. So we can improve that. We can't totally eliminate that, but we can improve that by putting a little bit of a chamfer there where the machined surface and the cast surface meet. This is going to be down to how well you dialed it in and just how good the casting is. So there's only so much you can do here, but a little bit of a chamfer on there definitely helps. I'm pretty pleased with that. Most of the machine work is done now, so time to pull the faceplate off, take it back over to the bench, and we got to flip this thing over and do the remaining little details on the other side. Pull all of that off, and the shims go away now because we're going to be clamping the machined surface down to the faceplate. And by doing this, we'll make sure that the opposite sides of the flywheel are coplanar with each other. Not that it really matters, again, it's all visual here, but certainly doesn't hurt. I set that up the same way, measured it, clamped it down, tapped it in, etc. Now I can machine the remaining features on this side, which includes facing the rim and then cleaning up all the surfaces on the center boss there as well. The big stuff is already done from the other side. Well, that is it for the major features on this flywheel. I'm pretty pleased with how that came out. Hopefully it's all going to look like it's running well once it's on the engine. However, now we've got that big center bore to deal with. We have to put that bushing in there. To start with, I take a lot of careful measurements of that bore. I want to know the exact dimension of that because I want to make a very accurate interference fit here on this bushing. I'm aiming for a 5/10 interference fit, and I mean dead nuts 5/10. I really want to nail that. So I'm taking my time here. I've got a very accurate measurement of the bore, and I'm making sure that this bushing that I'm making is to the 10th accurate all the way down the length, that there's no taper in it. I machined that carefully. Luckily my tailstock is well aligned right now. It's cutting very straight. And then I dialed in the last couple of tenths with some emery, focusing on areas where it was a little bit larger, and just making sure that once again I'm right to the 10th all the way down on this. It took effort, but that outer surface is really accurate. I'm actually pretty proud of that one. And now I can drill out the center here with a sequence of larger and larger drills, ending up at the pilot drill size for the 5/8 reamer, which is going to finish this out to the size of the crankshaft. My crankshaft is actually 1/1000th undersized, so the reamer should be perfect once we run that through there. Conveniently, I bought this reamer for the valve body, and it's going to get a second use here. So into the tailstock we go with this. Just slide that into the, just gotta open the, just gonna slide that into the, oh no, it doesn't fit. Don't panic, don't panic, don't panic. Just start taking apart other tools until you find something that will make this work. I dug out the manual for my Grizzly drill press and found that it has a 5/8 chuck and happens to have a Morse taper too in the spindle, same as the tailstock on my lathe. What good luck. So out with the normal tailstock Jacob's chuck, in with the one from my drill press, and now the reamer shank slides in there perfectly. Result. That is a lot of reamer on this little lathe, but we're going to make it work here. Finish in there is so-so. This is not very good steel that I'm using for this bushing, but that's okay. It's not a spinning part, so it doesn't matter very much. And Yahtzee. All right, there's the bushing. Quick test fit on the crankshaft to make sure it's a good fit, and it is. Very nice sliding fit on there. Now, it should not fit into the flywheel if I did my job right, but it should feel like it just wants to start because it's only 5/10 oversize, and that is just about right. That feels good. Now, I could try to press this in, but I want to be nice to this casting, so I'm going to try a lower stress way, which is a shrink fit. So for a shrink fit, you either heat up the outer part or chill the inner part. For the size of parts I have and the interference I need to clear, I need about 50 degrees of temperature difference between the parts. Now it's a lot easier to heat something 50 degrees than it is to chill it 50 degrees. However, I don't want to heat up that casting if I can help it, because I don't want to risk distorting or cracking it. Instead, I went and got some dry ice. There's two different ways that people use dry ice for this type of thing. The dry method and the wet method. I'm starting with the dry method here, which is where you just sandwich the part in some blocks of dry ice and let it sit for an hour. While that's chilling, I put some Loctite in the bore just for good measure. And let's get this thing out and see if we can drop it in there. Unfortunately, it started to go in, and as soon as it touched that casting, it immediately warmed up and got stuck. So I couldn't get it out again either, so I immediately ran over to the press, which I had set up on deck just in case this happened, and pressed it in as hard as I could. And I got it pressed 2/3 of the way in, and it got hopelessly stuck right where you see it here. Now this has happened to me before, and typically what you can do is just heat up the hub around that a little bit, and it's usually enough to where you can finish the press. Unfortunately, I spent quite a while gradually heating this up and applying heat to the entire casting to heat it up as evenly as I can. Differential heating is a surefire way to crack a casting, but I just could not get it to move. It was thoroughly stuck. So, plan B. I made a second, smaller bushing to fill in the remaining third of the bore, and I'm going to chill this one with the wet method. I've got isopropyl alcohol here. People also use acetone for this. Any liquid with a freezing temperature lower than the dry ice will work. Put the dry ice in there, make a solution, and drop the part in there. This is supposed to be more effective than the dry method because a solution has much more contact with the part, and it will conduct the heat out of the part much more effectively. You can see how it's kind of a slurpy here because the dry ice is pretty close to the freezing temperature of isopropyl alcohol, but it does not quite freeze. So I left that in there for an hour. Once again, in goes the little bushing, and if I'm quick, hopefully I can just drop this right in there. And once again, I tried and I messed with the alignment, and I tried and I tried and I could not get it to go in there. So once again, I ran over to the press and was able to press it home. Now I will say the press was quite a bit easier than would be expected, so I think that the chilling was definitely helping, but I had not succeeded in getting it cold enough to where it would just drop right in. It's not too shocking that this didn't work. The temperature of dry ice is right at the limit of how much shrink I needed, so if I'd gone the heat route, it would have been pretty easy to heat this casting up in the oven to 100 degrees, and that would have probably worked, but again, I was trying to avoid heating the casting. So a bit of a comedy of errors there, but in the end, I did get it to work. And then I just had to put it on the faceplate again and face those bushing stubs back down flush there. You can see lots of run out here because I didn't bother dialing it in for these facing operations. Dialing things in on the faceplate is pretty time consuming, so I don't do it if I don't have to. Now we need the keyway in the bushing there to match the keyway in the crankshaft. For that I've got a keyway broach, however I need to make the center bushing there because of course keyway broach kits never come with the exact combination of keyway size and bore size that you need, so you always end up making one of these bushings anyway. I suppose these keyway broach sets are fast if you have a lot of the same bore to do, but for one-offs you end up making the bushing every time anyway, so I don't think they're very fast. But hey, once you do have the broach, it's certainly quick and easy. Lots and lots of cutting lube on the broach there for the vitamins, and in we go. This size of broach uses 2 passes. You go through once with the broach in its birthday suit, and then you go through again with a shim behind it to move it outwards a little bit. Smaller broaches than this often use no shims, and larger ones may use multiple shims. The end result is certainly nice though, and it looks like I did the math correctly on the depth there that I needed for the bushing, so I'm pleased with that. Now I do need a key for this keyway. I didn't actually have any key stock the right size, so I grabbed a piece of square bar there and just milled it down. We have one last feature to do, and that's a set screw that holds that key in place. This is surprisingly tricky, once again, because of the size of this flywheel. I need to set it up at a 15-degree angle so that the tooling can reach into the center of the hub there. I'm using my trick angle table for this, but if you don't have such a fancy tool, you can also do this with some shims and a regular angle plate. I showed that approach on the previous engine that I did, so go check out my playlists for the PM1 engine. I'm going to reuse my clamping bars there once again, and unfortunately I have to do this on the back of the mill here because I don't have the Y travel to do it on the front, which means I'm doing all this via inspection mirror. I have to start by setting the keyway in the vertical position, just doing this by eyes close enough here. The goal is just to make sure that the set screw lands on top of that key. It doesn't have to be perfect. And I've got a piece of drill rod there, which I'm using to center up the spindle above the keyway. Now, of course, none of my tooling is long enough to reach down there either, so over to the lathe now. I've got a piece of ground stainless round bar in here. I'm drilling a hole in one size to be a good slip fit on my longest center drill. And then I'm going to flip that guy around, and I'm going to do the same thing in the other end, but down here I'm drilling it out to be a close fit on the tapping drill size that I need. And thus I've made a double-ended drill extension. I'll start with the long center drill in there. That's just Loctited in there. I had hoped that the center drill would be able to start the hole here on the top crown of the boss there, but unfortunately with the drill extension in there, it's just too flexible, and the center drill is wandering off the top surface. I had to give it a little help, which I did with a center punch right where I want the hole to start. And now the center drill was able to catch there and start the hole nicely. A little bit of heat will release the Loctite on the center drill, and there was some air trapped in there, so it ejected itself rather forcefully. Normally that's a low drama situation. You don't have to worry about overheating the drill there. The amount of heat required to release the Loctite is vastly less than the red heat that would damage the temper in the drill. Got to cool that down before I can put more Loctite in it, because of course the heat would damage the new Loctite. Then a little bit of Loctite on the tapping drill, and I slide that in the other end. Let that set for at least 10-15 minutes, make sure it's good and strong. And then I can go in there and catch my center drill there and drill that tapping drill size all the way through into the keyway. And that went really well. Next I had to tap the hole though, and I don't have a pulley tap, which would be the ideal tool for this. It's exactly designed to solve this problem. So instead I'm using the small end of my drill extension as a tap follower on the pointed end of the tap there. And then I have the smallest wrench I own, which is 5/32, and this was just the thing to turn that tap by hand while applying a little bit of light pressure with the quill to keep the tap straight. The reason I own a wrench this tiny is because I also work on pinball machines, which have a lot of tiny hardware in them. I think this is basically a mechano wrench too, so if you have a mechano set around, one of those wrenches might work for this. Okay, let's put it all together. There's the key that I made. That's a nice slip fit into the keyway there. I don't want it to get stuck, so it's a slip fit. And then the flywheel should slide over top of the key. Yes, very nice. Hopefully I got the length correct there, so it should line up flush, which it does seem to. And then in with the set screw, which holds the key in place. Get that snugged down. So the key is doing all of the load. The set screw is just keeping the key from sliding out of place. And there she is. That's one flywheel on one steam engine. That seems to run really well. I'm very, very pleased with that. Now, I'm not going to claim there's zero run out in this. There never is zero. If you look closely, there is some visible run out there, which I think is actually coming from the crankshaft. I think my crankshaft is not perfectly straight, but you know, it's never going to be perfect, and I learn a lot every time I build one of these engines. It doesn't have to be perfect as long as you learn something doing it and you're having fun. That's what counts, and I am definitely having fun making this engine. I think that's going to run really well. That's the flywheel, and like everything else on this engine, it was a bit of an ordeal because of the size of it and all the other little complications that came up along the way. I hope you enjoyed watching me solve these problems. I hope this will help dispel your fear if you're thinking about building an engine like this. Give it a try. If I can do it, you can do it. Thank you very much for watching. Thank you very much to my patrons who make all of this possible, and I will see you next time.